The final theorem we discuss in this section is the theorem called logical equivalences. This table that you're seeing on this slide is directly from your notes and also from the book. So don't worry about trying to copy it all right now. It's already printed in your book, so you could just refer to it. And I'll tell you the page number in a second. But basically, this gives us logical equivalences. And most of these can be proven using truth tables. So for instance, earlier in this section, we proved that P or not P is a tautology. We also proved that P and not P is a contradiction. And we did it using a truth table. Now, a lot of these other ones can be used when other letters are replaced with the letters that we have on this slide. So for instance, it doesn't have to be always P or Q. You can have, other letters and the commutative law still works. And there are two versions of the commutative law, one for the wedge symbol, one for the V symbol. Most of these have two versions for the wedge and the V. Take a look at this table and try to memorize as many of these as you can. Some of them are pretty intuitive. For instance, the double negation law says that negating the P twice results in the same value as P itself. So that's kind of a known one. We discussed it earlier in another video. Now, how do we use these logical equivalences? We use them when we try to prove that certain logical equivalences are true. So in another video, I said that we can do it with a truth table. In this video, we can show that two statements are logically equivalent by deriving the logical equivalences from the table that we just mentioned. And the way it's going to work is you're going to have to start from one side of this statement and try to get to the other side. Typically speaking, I like to start with the side that looks more complicated. So in this case, the left-hand side. And I try to simplify it as much as possible using the rules to get to the right-hand side somehow. So I begin with the LHS, which is left-hand side. I copy that down. And I try to figure out what I could do to manipulate it in order to make it somehow give me the right-hand side. So the first things first, I'm noticing that there's a negation in front of the first set of parentheses. So I could try to use De Morgan's law to distribute that negation. So keep in mind that negations turn the conjunctions into disjunctions, and you're supposed to negate both sides as well. So typically speaking, I like to do one step at a time, writing down the number of the rule that I used or the name of the rule that I used. In this case, I used De Morgan's law. That's why you're seeing the words De Morgan on the side. Once that's done, I can now use the double negation law to clean up and simplify the first part of this expression. The negative P can be turned into a P, and that's using the double negation. Once I do that, I notice that there's a P or in the first parentheses and another P or in the second parentheses. So using the distributive law, I can factor that P or and put it first, and then dump everything else into the second parentheses. The not Q that's left over, the Q that's left over, together with the symbol and that was in the middle. That's basically called the distributive law. It allows me to pretty much factor expressions. Now, in a table, we know that Q and not Q can be simplified. Not Q and Q. So I need to rewrite it using the commutative law so that it says Q first and not Q afterwards. Because then I could take advantage of the rule that says that Q and not Q is a contradiction, and that rule is called the negation law. And finally, P or contradiction is equivalent to P using the identity law, which finally gives me the right-hand side. And this is what I needed to show, so I'm basically done with the problem. See if you can do the same process for this expression. Start, if you can, with the left-hand side and try to get to the right-hand side somehow using the laws from the table that I gave you. So it's a good idea to pause the video here and attempt that for yourself. So again, I'm starting with the left-hand side, so I copy it down so that I know what I'm manipulating. And the very first thing I'm going to notice is that there's a De Morgan law that could happen over here. I can give this negative to everything inside the parentheses. And when I give the negative to everything inside the parentheses, the OR statement that was there turns into an AND statement. And I gotta negate both sides of the statement. So De Morgan's law, then I do a double negation on this Q to turn it into a regular Q. Once I do that, I notice that there's a not P in front and not P in the second parentheses that can be factored. So that's why you're seeing not P getting factored. So once the not P goes away, it carries with it the AND symbol that was in front of it. So that's why you're seeing that next. And whatever's left gets dumped together into a second parentheses. So the Q, the OR, the not Q get together inside the second parentheses, and that's called the distributive law. Now, Q or not Q is an example of a tautology. That's using the negation law. And finally, not P and tautology is equivalent to not P using what's called the identity law, which is the right-hand side, and that's what we needed to show.